what a dot product is, and if any of you found the Wikipedia page about dot product, anyone find this? Yeah? Dot product is the sum of the products of the corresponding entries of the two sequences of numbers. Now we're going to break that down, okay? And this will be the basic math we're using today in a little bit when we put matrices into play. But let's say I had two sequences of numbers. Like let's say I had this. These two sequences that represent, doesn't really matter so much right now. I'm just going to show you how to do the math. We're all agreed, though, that that is two sequences of numbers, right? Okay, so that's that part of the definition. The dot product is when I take the sum, and in math, SUM sum means to do what? Add, okay. The sum of the products, what does it mean when I'm taking a product of something? Multiplication, right? Okay, it means multiply. We're going to be multiplying some stuff. Of the corresponding entries. When we talked about corresponding entries before? Like, when did we do? Did we just talk about those last week? We did. We were talking about corresponding entries on matrices. What were we talking about? What does so like, look at this I will statement over here. I have these two matrices. If I pointed out this 2 right here, what's the corresponding entry over there? 3. What if I was pointing at this 4? What's the, oh, that 2. That one's missing a third column, so it doesn't matter. But that would be the corresponding entry. In this sort of example right here that I'm going to show you what a dot product is. A dot product is when you're multiplying two sequences of numbers, but you're multiplying the corresponding entries. So here is a 3. Which do you think is the corresponding entry over there? -5. So I'm going to take the product of those corresponding entries, which means multiply those two things. And then when I look at the 6, what's the corresponding entry to 6 over here? Okay, 7. I'm going to take the product of those corresponding entries, and then I'm going to do what with them? Add them. Okay, this is the sum of the products of corresponding entries. So that would be -15 plus 42, which I'm not sure. I think it's 27. Okay, so that gives me one answer. But if everyone in the world was following that pattern of a dot product, they would know that that 27 meant a certain thing that they were all talking about. Right? How this is going to relate to matrix multiplication today is I will have a sequence of numbers like this, 3, 6. And I'm going to multiply it by another sequence, -5, 7, but it's not going to be horizontal. It's going to be vertical. Why do you think that is? Because this would be the what of a matrix, and this would be a column, okay? Michaela, would you read me the thing that you found when you were Googling, please? What did it say for matrix multiplication? All right, perfect, thank you. So what we're going to be doing today for matrix multiplication is we'll have a matrix times a matrix. We will be finding the dot product of the rows on the first matrix and the columns on the second matrix. So that we're going to be finding the dot product of the rows of the first and the columns of the second. And so if I were finding this dot product here, all I've changed is I've made the second thing a column. It would look like this. Multiplying the first positions together, 3 times -5. Multiplying the second positions together, and then adding them. Okay, and then that one number is going to be part of our answer matrix. And so this was pretty straightforward, but how do you feel like that, and like what's the main difference between that and this over here? It's harder. It's not that it's harder. It's going to be what? Just a lot more product. Yeah, a lot more work. But that's the basics. If you can do that, you can do this. It's just going to be multiple times, all right? While I pass back your homework, pass out your notes. Did anybody do the homework? Okay, excellent. Are there any questions on the homework? It's really straightforward. So if you weren't here Friday, we added and subtracted matrices. We did scalar multiplication, where you multiply by a constant. The difference of multiplying today is we're doing a matrix times a matrix. But multiplying by constant just means everything inside got multiplied by that constant. This is what this week looks like. What are we doing in class tomorrow? We are doing a quiz. Today's work is not on the quiz tomorrow, okay? So if you look at the calendar, tomorrow's quiz is over Wednesday, Thursday, and Friday's work, okay? And this is your courtesy announcement to please put your phones away now. Thank you for looking at that stuff. I really wanted y'all to see some of the results, like how these kinds of math things are used in higher applications. I want you to begin, once you get your notes, and read this upper left-hand corner of your notes. So take a minute and just read those to yourself with your eyeballs quietly and just sort of absorb that. It's okay if you don't really know what's going on, I will tell you. It says in order to multiply matrices, the number of columns of the first matrix must match the number of rows of the second. This is probably the most important piece. I want you to, annotate it. So on Friday, when we talked about adding and subtracting matrices, what had to be true about the dimensions before you could add or subtract? They had to be exactly the same. Okay, that's because you were adding or subtracting corresponding entries, so they had to be exactly the same, so they had something to correspond to. Well, multiplication works a little bit differently. We are going to be doing dot products. And so the dimensions don't have to be exactly the same, but what has to be true is that the columns of the first have to equal the rows of the second, because we'll be doing columns by rows, and so if they're not the same, you'll run out of columns or rows. And that'll make more sense to you later. This mn and n and p, those are just general forms. Those are variables. It's kind of like when I give you Pythagorean theorem, a squared plus b squared equals c squared. You know that a, b, and c are variables, and you plug in whatever numbers you need depending on the problem. Well, that's the same for this m and this n and this n and this p. But what I'm about to write down, I absolutely want you to write down in your notes. Okay? Yeah, and I'm about to write down here. This says if matrix A has dimensions m by n, so I'm going to just write that underneath. Then in order to multiply it by matrix B would need these dimensions, n by p. What's going on with both of them having an n as part of their dimensions? What does that imply? I didn't understand, sorry. Not that they cross. If n, the columns here are n, the rows here are n, why are they using the same variable? Because they have to be the exact same, all right? So every time you're setting up a matrix multiplication problem, when I show you an example, this is what I'm going to be doing. Before I do any math at all, I'm going to put their dimensions side by side and see if these two things are the same or not. It's just a little short visual to help you remember what to do. This is saying that the columns here have to equal the rows here. And then there's this other nifty little thing, which from right here, the dimensions of the new matrix. And instead of new, I like this better, your answer matrix. I mean, it is new, but more specifically, I'm concerned that you understand it's your answers, the matrix with the answer. The dimensions of the answer matrix will be these. It'll be m by p. Okay, it'll be the rows of the first and the columns of the second one. And when we actually do an example, this will sort of all come together for you. Does anybody need that up anymore? Bless you. This part of your notes is important. It says matrix multiplication is not commutative. Anyone remember what the commutative property says? All right. The commutative property says that basically order doesn't matter. And that's true for integers when you're doing addition, subtraction, multiplication. So, for example, if I asked you, what is 6 times 3, what would you tell me? But what if I said, what is 3 times 6? What would you say? It's the same, right? Whether you do 6 times 3 or 3 times 6. The order for multiplication doesn't matter. The order for addition doesn't matter, too. Like 2 plus 4 is, and 4 plus 2 is. Okay, this is not true for matrices, which is what this part of your notes is saying. Matrix multiplication is not commutative. So the order of the matrices is important. So matrix A times matrix B doesn't equal matrix B times matrix A, except maybe sometimes on accident. But it's not a rule that you can count on. In fact, sometimes one order can't even be done at all, and the other reverse order can, depending on the dimensions. And then this says to find the entries of your new matrix, you multiply the ith row of A with the jth row of B by summing the products. Now that's really fun to say, ith and jth. Really, this is telling me that I'm doing the dot products. Okay, on the rows of the first matrix and the columns of the second. So having set all this up, let's do some matrix multiplication. Okay, blah. All right, so I've got 3 matrices. I've got 2 examples we're going to do. One of these examples will not work because of the dimensions, and I don't want you to holler anything out. All I want you to do before you do even any math, compare the dimensions on A and B, parts A and B, sorry, not matrices A and B. Do the little dimension thing I was showing you and figure out which of these you can't even do anyway. So take a moment to do that. So again, always compare your dimensions before you do any math at all. Because there's a lot of tedious math to do only to figure out 10 minutes later you didn't have to do it anyway because it's not possible. So A, the dimensions are 2 by 2, just like Noah. And B's dimensions are 3 by 2. Do those match? Okay, so this is an NA for not applicable. The columns of the first have to equal the rows of the second. The dimensions of C is 3 by 3. So I'm moving over to B now, part B. And the dimensions of B are 3 by 2. Do those match? Yes, that means we can do the math here. And by the way, you may not have caught this earlier. What will be the dimensions of my answer matrix? 3 by 2, that I can already tell. This is going to be the rows of your answer matrix, and this is the columns. Now, kind of put your pencils down for a second because I want you to see what I'm about to do. Whenever I'm beginning my problem, I check my dimensions, and then I set up my answer matrix a particular way that will help me keep everything straight as I'm working. I'm going to give myself a 3 by 2 blank matrix with answer lines that I will fill in as I go. 3 rows, there's my 3 rows, and there's my 2 columns. And the reason why I do that is because once you get into the middle of these problems, it's very easy to get lost and be like, what piece was I working on and which answer am I trying to fill in right now? It's very easy. You don't have to do this. This is not required. I highly recommend it, and I will do it every time I do these matrix multiplications. But you absolutely do not have to. All right, so let's begin practicing our dot products. I'm going to write, by the way, which matrix am I going to write down first? C. Does it matter the order I write them in? Absolutely, okay. So matrix C is, I'm going to write down, and you might want to work on the back. I gave you a lot of empty space on the back. There's not much on the front. We're going to do this first one in lots of detail. So if that is helpful for you, you will probably like to work on the back because it will take up some space. Times B. All right, so if we're doing dot products, we're multiplying the rows of the first one by the columns of the second. And so here's how this will go. Just like the example I gave you earlier, I said position ones, the product of the position ones, multiply position ones, multiply position twos, add them together. But in this case, I have 3 positions. I am going to try and find this answer first, this part of my answer matrix. What position is that when I'm talking about rows and columns? What position is that? It's row 1, column 1. So when I go to my matrices I'm multiplying, I look only at, right now, row 1, column 1. If I was trying to find this answer spot right here, the bottom right, I would be looking at right now row 3, column 2. Okay, so that's how your answer matrix corresponds to the ones you're multiplying. If you're trying to find row 1, column 1, you're finding the dot product of row 1, column 1. And here's how that looks. The dot product means you multiply position 1s. What's position 1 here? And position 1 here. Okay, so you multiply those together, 2 times 3. What's in the second positions of both of those things? -2 and -1. Second position here, -1. Second position here, -2. We're finding the product of those. What's in the third positions? 2 and 5. So multiply those together. So we're finding those products, 6, +2, 10. And then what do I do with those products? Add them. It's the sum of the products of the corresponding entries. So these are my products of my corresponding entries, and now I'm going to add them. And that gives me just this one piece right here of my answer matrix, 18. Now you are welcome to find your own pattern that you like to fill in your matrices. I like to just stay with the first row and move over to the second column. So I'm going to find this piece right now. Okay, which row is that? Row 1, column 2. So my matrices that I'm multiplying, I need row 1, column 2 now. And I'll find the dot product of those. I'm multiplying the numbers in the first positions. First positions are 2 and 0. What's in the second positions? -1 and 1. And what's in the last positions? 2 and 2. So I find those products. It's 0, -1, 4. And I do what with those 3 things? Add them. -1 plus 4 plus 0 is 3. Okay. So I want you to take a few minutes and try that. Try that with the rest of the rows. Remember that whichever space on your answer you're trying to fill in, You figure out the position, like row 2, column 2, and that's what you're looking at on your matrices, row 2, column 2. So real quickly, I'll do one more entry, and then I'll just tell you what the answer is supposed to be, okay? So you don't have to see me do all of those. You don't want to see that. Now, you might have had a pattern that you were following, but I want to show you that you can do it in any order that you want as long as you understand the concept. Like, for example, I normally go like this. Here, 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 here. But I'm just going to show you I can do randomly whichever one I want. Like, let's say I want to do this one first. Okay, I want to fill in that answer. Which row in column is that position? Row 2, column 2. So over here on these matrices, what am I going to look at here? Row 2, and here I'm going to look at column 2. So it's always the rows in the first one and the columns in the second. Just like the way you do your dimensions. You do rows first, columns second. And then I'll do the dot product of that. So I've got multiply the first positions are zeros. The second positions are 3 and 1. The third positions are 0 and 2. And I'm going to add those together. So that's 0, that 0, and 3 times 1 is 3. And I can put that there. Okay? So for me, and the way my brain works, as long as I have this answer matrix set up, I really could get lost. It's very easy to find myself again. For me, without that answer matrix set up like that, if I get lost, I'm kind of like, I don't know where I was. So anyway, and then this is what you have in the other spots. 6 and then 10 and 10. Who got those right? Okay, very good. Very good. Excellent. Negative 6. Yes, thank you. Okay, negative 6. Does anybody need this up before I change the screen? We're going to do this last bit of examples. First thing I want you to do is compare the dimensions and raise your hand when you figured out which one doesn't work. Thank you, 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 thank you. So who found that the first problem doesn't work? Did anybody find that the second problem doesn't work? Okay. The first one will work. The second one won't. Does anybody who found that the first one doesn't work, is anybody willing to volunteer what they wrote down for their dimensions? Because someone else might have made the same mistake and we could talk about it. Anyone? Someone? Tell me one more time, I'm sorry. Okay, so let's look at that. Thank you. So B is definitely 3 by 2. And am I on the wrong side of my notes? That seems like it works. Oh, no, I said yes. Oh, no, I mean, did anybody say that this one doesn't work and want to tell me, thank you, what their dimensions were so we can talk about the mistake? That's what I'm thinking. If you said that this one wasn't going to work, you probably switched it somewhere. Remember, it's rows here, columns here. And then we are checking that these match, and they do. Right? And what will be the dimensions on the answer matrix? 3 by 2, very good. And then the reason why this problem isn't going to work is B is 3 by 2 again, and C is 3 by 3. And those don't match. So we won't be able to do the dot products because we will run out of corresponding entries. They won't match up. So take a minute and set up your B times A. Who is going to be paying attention to the order that they write that in? Please, everybody raise your hands. Okay, thank you. Write down your B first. Then your A. And I recommend also setting up your answer matrix, which is going to be 3 by 2. 3 rows, 2 columns. Okay, take a minute and do your dot product.